Alright, this video is going to be on projectile motions. And you've kind of done a little bit of work with projectile motions, even though we didn't call them projectiles, when we were talking about objects being thrown vertically or when they were being dropped. Because basically, a projectile is any object that's shot through the air. Gravity causes the object's path to curve downward. Okay, so I'm sure you've seen some Looney Tunes. And hopefully you recognize that while it was funny to watch when we were a kid, that is not the true motion that Wile E. Coyote would go if he were to actually fall off the cliff. Okay? If we had a gravity-free path, that would be the motion, straight out. Here's a little canyon, here's our cliff. So if there was absolutely no gravity, this would be our motion. However, since we know there is gravity, our motion is actually like this. So our actual projectile motion is going to be more of this curve here, okay? Because we do have some horizontal velocity going, but as soon as it starts coming out, gravity is going to go ahead and start pulling it down. Okay. Another example would be kicking a ball off a cliff or off a deck or off the roof if you're into that kind of thing. Okay. We have, of course, a height. We have a vertical component, but we also have this horizontal component. So when we have this horizontal projectile motion, we actually have two components. This x, of course, means distance. When we have the subscript y, that's talking about the distance in the vertical motion, whereas here we have distance in the horizontal plane, so x sub x. When we're doing these kind of problems with this horizontal projectile motion, it's actually easiest if we actually break down the motion into those two dimensions. The horizontal, which is x, and the vertical, which is y. And then from there, we list all the things that we know. So this goes hand in hand with our kinematics problems, with our acceleration and our velocity. So those are going to be the kinds of things that we look for. X sub x is going to be the distance, and again, that's in the horizontal plane here, and that's measured in meters because it's a distance. V sub x, V, remember, is velocity. In the horizontal direction, it is constant because gravity does not work horizontally. Gravity only works vertically. Okay, so there's nothing really in the horizontal playing field that's going to change our velocity. So we actually have no acceleration horizontally. And then, of course, we have time. In the vertical field, when we look up and down, that's going to be a little bit more complex. XY is still our height. It's still our distance, but now we call it height because it's vertical. Our initial velocity, vertically, so y means vertical. And remember, this 0 means not, so the initial, or the not velocity of not in the y direction is actually going to be 0 meters per second. Okay, because from the very split, not even a full second when it gets off the cliff, there is no velocity in this y direction until gravity starts pulling on it. However, the final velocity, that instant right before it smacks on the ground, the velocity in the y direction is not equal to 0. Okay? Of course, we know acceleration is due to gravity, which is negative 9.8 meters per second squared. And then, of course, we still have time in the vertical direction. Now, if you remember from the video at the beginning of today, that little video and little assignment question in the video, whatever you want to call it, is that the time vertically, if something is just dropped, is going to be the same as if something is launched. So time is going to be the same. And this is key because this component is going to be what connects these two aspects of horizontal projectile motion. Okay? For example, Let's say we have a ball rolls off a 1.5 meter tall table with a speed of 3.2 meters per second. And we want to know, when does the ball hit the ground? Okay, so first we need to just analyze the information we're given. We know it's going to be rolling off this table, so we know we're going to have some kind of path like this. So we need to split the components of this problem into the x and y. So in the horizontal direction, our xx, we don't know what it is. I don't know what this distance is. My velocity in the x direction is 3.2 meters per second. Okay, so it's rolling off at 3.2 meters per second. There is no acceleration, and I don't have a time. Okay, so let's look if we have anything in the y direction. xy is 1.5 meters. It's a 1.5 meter tall table. I know my initial velocity in the y direction is going to be 0. I don't know what my initial or my final velocity is in the y direction. I know acceleration is negative 9.8 meters per second squared, and I don't know my time. In fact, my time is going to be what I'm looking for. When does the ball hit the ground? Okay, so if we look at how I broke up the information, I don't have enough information here to find time. But if I look on my y side, I'm like, okay, I have 3 components. So if you remember when we did our kinematics, so let me see if I can pull that up real quick. When we were looking at these equations, I have these 4 equations here, and so I need to think about, well, which one am I going to use? And I realized the only thing I didn't have was this final velocity, so it ends up that that's going to be the equation that we're going to use. Okay, so I have an initial velocity, I have an acceleration, I don't have time, but I do have a height. So we are going to have to rearrange this equation since I am looking for time. This part, this v naught t, is going to be, we can ignore it since our initial velocity is 0, and anything times 0 is 0. So that's just going to leave me with x equals at squared over 2. I need to get t by itself, so I'm going to multiply by 2 on both sides, so I get 2x equals at squared. I need t by itself, so I'm going to have 2x over a equals t. And then I ran out of room, but remember we're looking for t, not t squared. So I'm going to find the square root of this, find the square root of that, and then just plug in the information. 2 times 1.5 divided by negative 9 divided by 9.8. At this point, the negative is irrelevant. We take the square root of that to get t, not t squared. And it turns out that the ball hits the ground after 0.55 seconds. So in less than a second, the ball will hit the ground. If we have this same problem, so notice I just transferred the information over, but this time we're going to be looking for, well, how far away from the base of the table is that ball going to land? Okay, so when I look at this, I just transferred the information. We calculated 0.55 seconds in the last problem. Time is the same. Vertical, horizontal, that's going to be our connecting piece. So the time is the same here. And now if we look, I have a velocity, I have the time, I'm looking for this distance because I want to know this horizontal range. How far away from the table does it land? This one's a little bit easier because I just used my constant velocity equation. There is no acceleration, so I have v equals d over t. Except I'm looking for the d, I'm looking for the distance. So I'm going to have to multiply by t, so I have v times t equals d. Plug in my numbers, and so that ball is going to land 1.77 meters away from the base of the table.